Hey everyone! So in this video I like to talk about Taylor polynomials. So we saw that tangent lines can be used to approximate the values of a function near the point of tangent C. And so let's quickly draw a picture of this. And so here if I sketch out the graph of some curve, let's say this curve is given the name f of x, and we look at the tangent line at the point, let's just say x is equal to a. So here is just a rough sketch of the tangent line to this curve at x is equal to a. And we can see that near this point of tangency, near x is equal to a, this tangent line has roughly the same y values as our original function, and it has roughly the same slope as our original function. And so here this tangent line can do a pretty solid job approximating the values of this function f of x. And if we didn't really want to plug in to our original function to compute some outputs, using the tangent line would be a great replacement for approximate values. So near x is equal to a, the tangent line has almost identical y values to our original function, and almost identical slope, or first derivative. And actually, right at x is equal to a, so at the point of tangency, the tangent line has the exact same y value and the exact same slope. And so Taylor polynomials, which we'll really dig into as we get further into this video, they extend this idea of a tangent line to broader examples of polynomials. But here, maybe just to build things up, let's go through an example of finding the tangent line to a particular curve at a particular point. So let's find the tangent line to, let's say, f of x is equal to cosine of x at x is equal to pi over 3. And so how do we go about finding the tangent line to f of x? Well, here we can use point-slope form. Right, so here, if we take y minus the y value of the point on our line, right, so f of pi over 3, this is going to be the y value to, or the output value to our curve at x is equal to pi over 3. Right, y minus this y value times the slope, so here the derivative evaluated at pi over 3, so the slope of our tangent line, times x minus the x value of our point, right? So x minus pi over 3. So this is going to give us the tangent line to our curve at x is equal to pi over 3. So we're going to need to figure out some values, but let me just rearrange this so that that y variable is isolated. Let me add the y value f of pi over 3 to both sides, giving us f of pi over 3 plus f prime of pi over 3 times x minus pi over 3. Okay, so let's get some values here. So here maybe let's do some computations on this side. So here we need to figure out what f of pi over 3 is equal to. Okay, so this is equal to cosine of pi over 3. And so let's draw a quick unit circle. Right, so add an angle of pi over 3. So this is a 60-degree angle from our x-axis. Well, the output value of cosine is going to give us the x-coordinate of this point on the unit circle, and this is 1/2 in our 30, 60, 90 triangle in the unit circle. Right, so here f of pi over 3, this comes out to be 1/2. But this isn't the only thing we need for our tangent line. We are also going to need the derivative evaluated at pi over 3, right? So we're going to need f prime of x. And so what's the derivative of cosine of x? Well, that's negative sine of x. And so what's negative sine of x evaluated at pi over 3? Well, sine gives us the y value of our coordinate at this particular angle. So here we're looking at that same angle, pi over 3, and we're looking at the y value of our point on our unit circle, and this is square root of 3 over 2. And so here, f prime of pi over 3 is the square root of 3 over 2. This is the slope of our tangent line. And so here, if we go back to the equation of our tangent line, we have y is equal to, well, this was 1/2, right? Cosine of pi over 3, that's 1/2, plus the slope of our tangent line was the square root of 3 over 2 times x minus pi over 3. And usually we simplify this and we write this in slope-intercept form, but actually I think it'll be more illustrative for our later examples if we leave this equation in this form as is. And so this tangent line, right, we said that it has an identical y value to our function at x is equal to pi over 3 at the point of tangency, and it should have the same first derivative as our original function at x is equal to pi over 3. And maybe let's just really quickly verify that at x is equal to pi over 3, y is equal to 1/2, right? The output of our original function at x is equal to pi over 3. And then let's also verify that the first derivative of this new approximating function is going to be identical to our original function. Right, so the square root of 3 over 2. And so, if we check this first idea, right, verify that at this particular x value, this tangent line gives us the same y value as our original function. Well, if we imagine plugging in pi over 3 into this x value here, right, what do we get out? Well, maybe I'll just write this down real quickly. Down below, we get y is equal to 1/2 plus the square root of 3 over 2 times, well, we're inputting x is equal to pi over 3. Well, pi over 3 minus pi over 3 is 0. And so we're going to have 0 times the square root of 3 over 2. And we're just going to get back 1/2, right? So here, plugging in the x value of the point of tangency sort of forgets about this latter part of this equation and just gives us that original, that constant term in front, which was the output value of our original function in the first place. And so what about the first derivative? What does y prime look like? Well, if we look back to our original function, not our original function, this equation of our tangent line here, well, taking the derivative of that constant term gives us 0, plus, and then here, this is just a linear part of our equation. Maybe I'll multiply this out, right? So here, this comes out to be, right, this is 1/2 plus the square root of 3 over 2x minus the square root of 3 over 2 times pi over 3. And here, right, this is just a constant term, this is just a constant term, and so we're just left with the derivative of this square root of 3 over 2 times x. We really are just left with the square root of 3 over 2 as our derivative. And so if we plug in pi over 3 into this derivative function, well, we're just going to get back the square root of 3 over 2. All this to say that our tangent line has the same slope and the same y value as our original function. And it does a pretty solid job of approximating our original function near this point at x is equal to pi over 3. So what if we want a better approximating function near x is equal to a than a tangent line? So a tangent line is great. It has the same y value, has the same slope at that point, x is equal to a, but it's a little rigid. Right? So many different functions, they have some sort of curvature to them. And what if we used a function that was curved to approximate our original function? What if we used, let's say, a parabola or a quadratic function? Right? So that might look something like this. And there, I think this quadratic function or this parabola would do a better job than our tangent line of approximating the original function near an x value of a. And so here maybe let's extend our ideas of finding an approximating tangent line to finding a quadratic function. And so here what we're going to look for in this quadratic function is for it to have the same y value at x is equal to a, the same slope, the same first derivative, and the same second derivative. At x is equal to a. And so here maybe I'll just tell you straight up what this quadratic function is. So y is equal to, it looks a lot like the equation of our tangent line. So y is equal to f of a plus f prime of a times x minus a. So here this is identical to our tangent line equation so far. But then we have this additional quadratic part that we're sort of adding on. So here this will be f double prime of a divided by 2 times x minus a squared. So this is the quadratic part, and we can see that we've got x minus a squared, so when we expand it out we'll have x to the power 2 in there. And the coefficient of that squared part, well here it's f double prime of a, the second derivative of our original function evaluated at a, all divided by 2. So this quadratic function satisfies the conditions above. And so this might look a little scary. There's a lot going on here, but let's go through our previous example of y is equal to cosine of x. Let's look at that x value of pi over 3 again, and let's take our our tangent line, our linear approximating function, and tack on this quadratic part and see what it looks like. So how would this look for f of x is equal to cosine of x at x is equal to pi over 3? Well, we have the same things as before. So y is equal to 1/2 minus the square root of 3 over 2 times x minus pi over 3. So that was our tangent line that we found earlier in this video. And so what we need to do is we need to find f double prime evaluated at a, and then we'll be done. So here, earlier we had f of x is equal to cosine of x. We said that f prime of x is equal to negative sine of x, and f double prime of x, well, this is equal to negative cosine of x. And so we want to evaluate f double prime, our second derivative, at pi over 3. We want this function to have the same second derivative at pi over 3. And so here this is negative cosine of pi over 3. And we already evaluated cosine of pi over 3. We saw that that was 1/2. So what we get out of this is negative 1/2. And so our formula above says that what we have here is the second derivative evaluated at our x value. So it's going to be negative 1/2. Maybe I'll write it like this. This is negative 1/2. We have to divide it by 2. And then it's being multiplied with x minus a squared. And so here, this as a function, this here, this is our approximating quadratic function. If we plug in values into this function near x is equal to pi over 3, we'll get really great approximations for y is equal to cosine of x. So actually, this shouldn't be x minus a, this should be x minus pi over 3. I'm sure that's not going to be the last time I make that mistake with everything that's going on in these equations. Okay, so here, let me just rewrite one more time that this was just our tangent line part earlier. And we're just adding on this additional quadratic part. And so let's check that our conditions are satisfied with this new equation. Let's really verify that this is the right thing we need to add on to our tangent line equation to get this quadratic function with the same y value, the same first derivative, and the same second derivative to our cosine function at pi over 3. And so here, let's first off, let's check. So let's check that we get the same y value at x is equal to pi over 3. Right, so this y value was 1/2. And we can see that if we rewrite our equation out here, so y is equal to 1/2 minus the square root of 3 over 2 times, here we're plugging in pi over 3 for our x value, and we're asking what the output comes out to be, so I'm going to replace x with pi over 3. And then here we have negative 1/2 divided by 2. Well, I can rewrite that as negative 1/4, right? So 1/2 divided by 2, is 1/4. And we're, again, plugging in x is equal to pi over 3. And then squaring that part, right? So here, if we look at what we get from this function, well, the pi over 3 minus pi over 3, this cancels out, and we're left with just 1/2, like we expected. We get the same original y value. Let's check the first derivative again. So let's check that we get the same first derivative at x is equal to pi over 3. And so the first derivative that we got earlier was, what was it? I believe it was negative square root of 3 over 2. Well, if we look at this original function and we take the first derivative, well, we already took the first derivative earlier of this part. We saw that that came out to be, well, this constant term vanishes. We saw that we just got that negative square root of 3 over 2. And what we have left over to take the first derivative of is this quadratic part. So here, let me rewrite what we have down so far. So here this is y prime is equal to, well, we're going to lose out on that constant term. We're going to get negative square root of 3 over 2. And we also have to take the derivative of this quadratic part, which it looks like, here we'd have to apply the chain rule, right? We have this constant term, and then we have this, this quadratic term, which has x minus pi over 3 as the inner part of our quadratic expression, right? So this is a composition of a power function and the function x minus pi over 3. And so what we'd have to do is we'd have to apply our power rule, right? Bring down that factor of 2, multiply with x minus pi over 3, and then multiply that with the derivative of our inner function, which in this case, the derivative of this inner function, x minus pi over 3, that's just 1. Right? The derivative of x minus pi over 3 is just 1. And so here what we get is, we have that negative 1/4. We're going to bring down that factor of 2 from that power. Right? So 2 times x minus pi over 3, and then times the derivative of this inside of x minus pi over 3, that's just 1. Right? So this factor of negative 1/4 and 2, that comes out to be negative square root of 3 over 2 minus 1/2 x minus pi over 3. And so if we again plug in an x value of pi over 3, this part here would vanish. It would disappear, and we'd just be left with negative square root of 3 over 2 as the output when we plug in x is equal to pi over 3. So that's what we expected, right? We expected negative square root of 3 over 2 as an output when we input pi over 3 into this first derivative function, and that's what we're getting. And so we also expect this quadratic function to have the same second derivative. And we just saw that the second derivative of our cosine function, evaluated at pi over 3, well, that was, what was it? I believe it was a negative 1/2. And so if we take this first derivative function and we take the derivative of it again, well, that constant term vanishes and we're just left with negative 1/2. And so here, this part, it's this linear part, and the coefficient of that x term would just be negative 1/2. And so the second derivative here would just be negative 1/2. And so when we plug in x is equal to pi over 3, we get negative 1/2. We get the second derivative we're expecting. And so this quadratic function satisfies all of those different conditions. And so here, let's take a look at the graphs of all of these different functions. Let's take a look at the graph of our original function, f of x is equal to cosine of x. Let's look at the tangent line, and let's look at this new quadratic function and see how they all compare. So here's our original function, f of x is equal to cosine of x. And then here's our tangent line to this curve, which does a pretty great job of approximating our function. But then here's our quadratic function that we just wrote out, just determined. And here we can see that it does a much better job of approximating this curve than the tangent line, right? The distance between the black curve, y is equal to cosine of x, and the purple curve, the quadratic function, it's so much smaller than the difference between the original curve and the tangent line. And we didn't even have to zoom in all that much to see that our curve, our quadratic function, does a much better job approximating our original function. So earlier I gave you this formula for the quadratic function that approximates our original function at x is equal to a. It's this tangent line equation added on with this quadratic term whose coefficient is the second derivative of our original function divided by 2. And you might have wondered where this division by 2 comes from. Why is that there? And I didn't explain it earlier, but now that we've gone through one example and we've taken derivatives of one example, we can better explain this now. And so the idea is that we want this function to have the same second derivative as our original function, and this division by 2 is just to really guarantee that. Right? When we take the second derivative of this function, we'll have to apply the power rule, and this factor of 2 will come down. And so this division by 2 is just so that we cancel out with that factor of 2 there, and when we take the second derivative, we're just left with f double prime of a, and we'll match the second derivative of our original function. So we went over an example of a quadratic polynomial which nicely approximates the graph or the values of our original function near a particular x value. But there's no reason that we have to stop at a degree 2 polynomial. Actually, we can keep going and try and find a higher degree polynomial which even better approximates our original function near a particular x value. And so, right, what if we wanted a cubic polynomial that approximates our function f of x near x is equal to a? So earlier when we thought about a quadratic polynomial, well, we made some demands. We said that it ought to have the same y value, the same first derivative. Right, so this was the case for our tangent line, but then when we added the condition that it ought to have the same second derivative as well for this quadratic polynomial, so same second derivative. And here for a cubic polynomial that'll approximate our function, here we can make the demand that it'll have the same third derivative. And so earlier we said that for a tangent line, Well, it should look something in the form y is equal to f of a plus f prime of a times x minus a. So that was the equation of our tangent line. And for this quadratic function, we added on a single term. We said, okay, well, it's going to have the same second derivative. But here we had to divide by this factor of 2, so that when we apply the power rule, we end up with this f double prime of a. When we apply the power rule twice, we get the same second derivative. And so what would we expect here to be the coefficient of x minus a cubed, so that we end up with the same third derivative? Right, so here we're going to have f triple prime of a. But what should we divide by? So not 3 actually, but we should divide by 3 times 2. Right? If we were to take the third derivative of this function, if we were to apply the power rule 3 times, well, we would bring down a factor of 3 and a factor of 2. And so here we should have a denominator of 3 and a denominator of a factor, including a factor of 2, so that those would cancel out, and we'd just be left with f triple prime of a. And that our third derivatives would really match up with our original function. And so let's come up with this cubic polynomial for our cosine function. Let's do this one more time before we talk about this really in full generality. So here, we already figured out that for f of x is equal to cosine of x at x is equal to pi over 3, this cubic polynomial. So we already came up with part of it, right? We said that we've got 1/2 the original y value, take away the square root of 3 over 2, so this was the first derivative, times x minus, well, in this case, a is pi over 3, so pi over 3. Then take away the second derivative, negative 1/2. This is then divided by 2, so this is negative 1/4 times x minus pi over 3 squared. And now we need to add on the third derivative divided by 3 divided by 2, so divided by 6 times x minus pi over 3 cubed. And so here, let's off to the side, let's evaluate f triple prime of x. So here, when f of x was, maybe I'll rewrite this all the way out. So here we had f of x is equal to cosine of x, f prime of x, that's negative sine of x, f double prime of x, this is negative cosine of x, and then f triple prime of x, well, this is just positive sine of x now. And so if we're going to take this third derivative and we're going to evaluate it at pi over 3, well, we just get sine of pi over 3, which we said earlier was the square root of 3 over 2. So here we're going to get plus the square root of 3 over 2 divided by 3 times 2 divided by 6 times x minus pi over 3 cubed. And so here, square root of 3 over 2 divided by 6, that's really just the same thing as the square root of 3 over 12. So let me erase this and write that here. So this is plus the square root of 3 over 12. And so, just like we did before, let's check that this polynomial here satisfies those conditions. Let's check that it has the same y value. So if we evaluate this polynomial at x is equal to pi over 3, well, we're going to plug in pi over 3 here, here, and here, and all these terms past the constant term are going to cancel out. And we're just going to be left with 1/2. And so here we do get the same y value that we expected, 1/2, so this is true. What about the same first derivative at pi over 3? Right, so earlier we saw that it was, the first derivative came out to be square root of 3 over 2, or negative square root of 3 over 2. Let's see that we get the same thing here. So when we take the derivative of this function, we get y prime is equal to, we get negative square root of 3 over 2 minus, here we would have to apply the power rule, bring down that factor of 2 to give us negative 1/2 times x minus pi over 3 times the derivative of the inside, but here the derivative of the inside is just 1. And if we apply the power rule to this part of our function, well, we bring down that factor of 3, giving us plus the square root of 3 over 4 times x minus pi over 3 squared. Right? We bring down that factor, that exponent as a factor, and decrease that exponent by 1, but we still have that same inner function, x minus pi over 3. And then we have to multiply by the derivative of the inside, but again, the derivative of the inside is just 1. And so if we evaluate this at pi over 3, well, here all of these terms would cancel out, and we'd just be left with negative square root of 3, which was the value of our first derivative at pi over 3. So here we do get the same second derivative. What about the same, or sorry, we get the same first derivative. What about the same second derivative? Well, y double prime, here that constant term vanishes. We're just left with negative pi, or not negative pi over 2, negative 1/2 plus the square root of 3 over 2, right, using the power rule again. We bring down that factor of 2, that cancels out with the part of our denominator of 4. We're just left with x minus pi over 3 multiplied to the square root of 3 over 2. And so here, if we evaluate at pi over 3, again, this part cancels out, and we're just left with negative 1/2, which is the second derivative evaluated at pi over 3 of our original function. And so here, this checks out as well. And then one more time, our expectation was that we wanted this to come out with the same third derivative. Well, if we take the third derivative of this function, we're just left with the square root of 3 over 2, which we saw a moment ago was the third derivative of our cosine function evaluated at pi over 3. So this is a polynomial that satisfies all of our conditions, has the same y value, the same first derivative, same second derivative, and same third derivative. So now that we've come up with this new cubic polynomial that will approximate our function, let's see how it compares to the quadratic and the linear function and the original function. Okay, so here's the graph of f of x is equal to cosine of x. Earlier we saw this tangent line plotted out. We saw this quadratic function plotted out that did a better job of approximating our original function than the tangent line. And here is our cubic function that we just found. And so this cubic function, we can see that it hugs the curve a little bit better than our quadratic function. And so it does a better job of approximating the function near x is equal to pi over 3, and actually does an even better job approximating the function further away from pi over 3. And so there's the cubic function. We can, just like we've extended this idea from linear to quadratic to cubic, we can keep pushing this idea. And here I've got the degree 4 polynomial that approximates this function listed out. We won't have to go through all of the checking that we did earlier for our degree 2 and degree 3 polynomials here, but here's the degree 4 polynomial, and here's the degree 5 polynomial. And so we can see that here, these polynomials actually do a great job of approximating our original function. If we look further away, we can see that they really do get away from the graph, but near pi over 3, they do a really great job. And we get better and better approximations further away from pi over 3 as we use higher degree polynomials. And so actually, if you've ever wondered how a calculator evaluates something like cosine, which doesn't really have a formula for how you compute the output values, really it does something like this. It approximates the values of the outputs of the cosine function using either these sorts of polynomials, these approximating polynomials with higher and higher degrees, or it does something called the Cordic algorithm. And so here, this is just one of the examples of ways that a calculator might compute cosine, and actually this is how it might compute sine or values of the tangent function as well. So in all of our examples, we saw that we can obtain more and more precise approximating functions to our original function by using higher degree polynomials. And really, all these examples of polynomials that we use to approximate our original function, these are known as Taylor polynomials. And so let me define what a Taylor polynomial is. So a Taylor polynomial, right, so these are the approximating polynomials. These are polynomials that have identical derivatives to our original function at that particular point. So here, a Taylor polynomial, and we can be as precise as we want. Let me just use an example here of degree n. And so all these polynomials, they really approximated our original functions near a particular point. And so that point is usually called the center. So centered at x is equal to a. So this polynomial, it's a polynomial with the same y value as the original function, the same first derivative, the same second derivative, the same third derivative, all the way up to the same nth derivative. And so here we saw that we had to take f double prime of a evaluated at a, and we had to divide by 2 so that when we applied the power rule multiple times to this function, and we brought down that factor of 2 would cancel out with that division by 2. And then similarly here we saw that for f triple prime evaluated at a, we had to divide this by 3 and 2 so that when we apply the power rule multiple times, well, the factor that comes down from taking it once, that factor of 3 would cancel out with the denominator. The factor of 2 that we obtained by taking the power rule again, it would cancel out with the factor of 2 in the denominator. And this would be the case for all of the terms, all the way up to the nth term, right? So here we take the nth derivative evaluated at a. There would be this factor of x minus a to the power n. And this would be divided by, n, would be divided by n minus 1, divided by n minus 2, all the way down to 2 and down to 1. Right? When we take this derivative n times over and we get the factor of n, the factor of n minus 1, n minus 2, these should all get canceled out, and we should just be left with f, the nth derivative of f evaluated at a. And so here, this is typically referred to as n factorial. So here this is read as n factorial, and this is just n, maybe I'll write it the other way. This is just 1 times 2 times 3 times 4, all the way up to multiply with n minus 1 times n. This is n factorial. And this is what we would need in the denominator so that when we apply the power rule so many different times, all those factors we obtain from the power rule would get canceled out here. So this is the polynomial that has the same first n derivatives as our original function. So let's just do one last example. Let's find a degree 4 Taylor polynomial centered at x is equal to 1 for the function g of x is equal to ln of x. So we're going to need this Taylor polynomial to have the same y value and the same first 4 derivatives as this original function ln of x. And so let's find what these y values and these derivatives are. So g of 1, this is ln of 1. This is asking us what power of e is going to give us an output of 1. Well, any number raised to the power of 0 is going to give us an output of 1. And so here, e to the power of 0 is going to give us 1. And then here, g prime of x, well, the derivative of ln of x, that's 1 over x. And so g prime of 1 is going to be this function evaluated at 1, which is just 1. Now g double prime of x, well, this is the derivative of 1 over x. And 1 over x, that's the same as x to the negative 1. And so we can apply the power rule to get 1, well, maybe I'll write it this way, negative x to the negative 2, which is the same as negative 1 over x squared. And if we evaluate this at 1, this gives us negative 1. And then here we also need the third derivative, g triple prime of x, and we can apply the power rule to our above example. Bringing down that factor of -2 gives us +2, x to the -3. So this is 2 over x cubed. And if we evaluate this at 1, this gives us 2 over 1, which is just 2. And we just need one last example, so we need the fourth derivative. And so using the power rule to our previous example, we get -6x to the -4th, which is -6 over x to the 4th. And so if we evaluate this at 1, oh, I forgot to put my input variable here. If we evaluate this at 1, well, we just get -6. So here, these are the values we'll see appear in our Taylor polynomial of degree 4. So quite a few values, but let's start building this up. So here, this Taylor polynomial of degree 4. Oh, there's one thing I forgot to say. So oftentimes these Taylor polynomials, they're actually labeled by t sub whatever degree the polynomial is, so t sub n of x. So sometimes you might see these Taylor polynomials referred to in this way. And so if we're trying to find the degree 4 polynomial, the degree 4 Taylor polynomial for this function, we're trying to find t sub 4. But we saw that these Taylor polynomials are sort of built up in terms of all of the previous Taylor polynomials of lower degrees, and so maybe let's just build this up as we go. So here really this means t sub 1 of x, the Taylor polynomial of degree 1, well, this was just the tangent line. This was just g of 1 plus g prime of 1 times x minus 1. Right, x take away the center value. And so here this is 0 plus 1 times x minus 1. The tangent line that approximates our curve is just the function x minus 1. And then the quadratic function, well, it contains this part of this tangent line function. We have x minus 1 here, but we also have this factor, this quadratic term, that, well, it has the second derivative divided by 2 times x minus 1 squared. And then what about the third degree Taylor polynomial for this function? Well, here it has all of the previous parts. We'll write this as a -1/2 times x minus 1 squared. But it also has this cubic part, right? So it's going to be 2 divided by 3 times 2. So 2 divided by 6, which is just 1/3. So it's going to be plus 1/3 x minus 1 cubed. And the fourth degree Taylor polynomial, well, this is the same thing, but with this additional term added on. And so this term is going to come from taking this -6 and dividing it by, maybe I'll write it out. So it's going to come from -6 over 4 times 3 times 2 times 1. And this is negative, well, here I can see that this would come out to be 6 as well. And that would cancel out with the 6 in the numerator. This is -1 over 4. So this would have plus 1/4 x minus 1 raised to the power of 4. So this is the fourth degree Taylor polynomial of ln of x centered at x is equal to 1. So here's the graph of our function, ln of x, y is equal to ln of x, and let's compare the graphs of the different Taylor polynomials to the graph of this function. Let's see how well these Taylor polynomials approximate the function. So here's the linear function. Here's the tangent line. Here we've got the quadratic Taylor polynomial, the Taylor polynomial of degree 2. Here this is the Taylor polynomial of degree 3, which we can see is already doing a much better job of approximating the curve. And then here's the Taylor polynomial of degree 4 that we found. And so here we can see that this polynomial does a really great job of approximating near x is equal to 1 it falls away quite steeply from the graph, away from x is equal to 1. And this is something I should mention, is that for some different kinds of functions, as we use higher and higher degrees of our Taylor polynomial, the approximation will actually stay really good even far out, as long as we use a high enough degree. There's some functions where no matter how high of a degree you use, really there's a limit to how far this Taylor approximation, or this Taylor polynomial, will approximate your function still. And so this is one of those examples. Really, it's only valid really close to x is equal to 1, but we can see that near x is equal to 1, it does a great job.